to 5 hours, whatever happens. Okay, chalo. So today we are going to do problems on generalized heat conduction. Whatever we have done till now, we are going to solve questions based on those. Okay, we are not taking book questions because those are basically very elaborative. Okay, in gate questions, most of the data is given. In books, most of the data you need to find out. Okay, so we are actually practicing gate questions so that you will get an idea. Every time whenever you are studying the subject very first time, it is a good idea to solve previous year questions. Why? Because you should know, you will know that you are in the right direction. For example, you are doing the subject very first time, and you start solving book questions. So book questions are very elaborative. Okay, most of the data you need to find out from tables, from other sources. So in gate questions, most of the data is already given. So if you are practicing gate questions, you will know that what type of questions are asked in gate. So whenever you go back to books, at least you would know ki if this type of question comes, what data will be given in question. So you would have more confidence when you are solving book questions, because you would know that okay, this data must be given in question. Okay, and if you are able to solve previous year questions through the concept that we have covered in class, that means that concepts are already covered. Now practice part is up to you. How much ever you time, because gate is all about practice. Okay, even if I give 2 hours for each topic for practice questions, it will not be enough. Now you have to give your time for practice. Okay, chalo. So this is my brief introduction. I hope you all know me. Okay, I'm Tech and MSc from Politecnico di Milano, some teaching experience, and this is my AII score. Chalo. So we will start with the first question. Slowly read this question. I would always recommend people, for example, I am going to read the question, I am going to write the given, I am going to write what we need to find out, I am going to draw the diagram. But I would expect you to do it yourself on a piece of paper and answer before me. Before I solve the question, you need to answer before me. Even if you ever do it, you have done it once earlier, but again do it one more time. Okay, chalo. It is 2017 2-mark question. Heat is generated uniformly in a long solid cylindrical rod. So it is a cylindrical rod. It is a long cylindrical rod, okay, with diameter 10 millimeter. Okay, at the rate of, you see, what is this? Is it capital Q or is it small q? Tell me. Is it capital Q or is it small q? Small q, because it is watt per meter cube. Okay, so it is small q generation is equals to 4 into 10 to the power 7 watt per meter cube. Okay, the thermal conductivity is also given. Thermal conductivity of this rod is also given. Watt per meter Kelvin. Under steady state condition must need to be satisfied. The temperature difference between the center and the surface of the rod is. So what do you mean steady state? Steady state means whatever the surface, whatever the wall temperature here, it must not change. It must not change with respect to time. Okay, it must not change with respect to time. And anyway, it is a cylinder. So all the wall, like if you talk about the surface area, the outer radius at r is equals to r, capital R, everywhere t will be equal to tw. We already know this. And in this case, in the same case, we have determined already that the maximum temperature will be at r is equals to 0. R is equals to 0. We know this, right? We know this, isn't it? Now, we know this, right? You remember we did this yesterday. Yes or no? Tell me. Yes. Okay, this is the first case. This was the first case. Now, if you remember, we defined two equations. What? T minus T naught is equals to minus Q generation by 4k small r square, and tw minus t naught is equals to minus q dot generation by 4k capital R square. And then we divided this so that we found out the dimensionless temperature difference, how the temperature is varying in the case of heat generation. Okay, again you are revising the concept. That is why I said please do a revision first, so that you would have a clarity, and when we do in class you will have the third revision, no second revision, let's say. Okay, chalo. Now what is they asking? They are asking the temperature difference between the center. So at the center, what is the temperature? Temperature we know. What is here? Here R is equals to 0, and here R is equals to R. Okay, so what is the temperature at the center? What is the temperature at the center? Here temperature is T naught. Here temperature is TW. So what I need to find out? I need to find out T naught minus TW. So now the sign will change. Now the sign will change. 4K into R squared. Now I know everything. I know everything. Yes, sure. Yes, Sahil, that is correct. Very nice. That is what I want from you. That is what I want from you. That you solve the question before me. Very nice. I'm very happy. Okay. So Q dot generation, how much is this? 4 into 10 to the power 7 watt per meter cube. 4K. How much is K? 25 watt per meter Kelvin, and R square. R is 5 millimeter. So 0.005 meter square. Meter square. Okay. So you can cancel this meter. So it will be cancelled here, and watt will be cancelled here. So you will get, when you solve this, you will get 10. Okay. So now it is temperature difference. So whether it is in Kelvin or it is in degree Celsius, it does not matter. Yes, that is square. Very nice. Thank you. Okay. So when you do this, you will get 10 degree Celsius. Is it clear? That is what they are asking. 10 degree Celsius or Kelvin, it does not matter. Okay. Because you are talking about temperature difference. I hope you already know this. If you are taking single temperature, then you must have to take care of units. But if we are taking temperature difference, then you are taking in Kelvin or degree Celsius, it does not matter. The difference will come same. Okay. Chalo. Very nice. Is it clear? Tell me, everyone. Sahil, Shikhar, Sean, and Shruti. Tell me, is it clear? Okay, very nice. Clear. Okay. Chalo, let us move on to the next question. Okay, this is the question. What is the question saying? It is GATE 2021 2-mark question. Okay, so you see what we did a lot of derivations, we did a lot of not calculations, but we derived, we defined so many things. But in GATE question, you do not require that much information. Okay, if I only give you the temperature variation equation, you will be able to solve this. But it will not serve our purpose, because at least you should have the idea that what we did. So if they will twist the question in some way, you can start from the beginning. Okay, so chalo. Now what is it saying? An uninsulated cylindrical wire of radius 1 millimeter produces electrical heating. Whenever electrical heating term comes, that means there is some heat generation. Okay, because of resistance there will be some heat generated at the rate of watt per meter cube. Now tell me, what is this? 5? Can you tell me? Let me draw a wire. Okay, now usually it is what? If this is the length of the wire, so you have given q dot dash. It is watt per meter, per unit length, basically. Okay, it is heat transfer. 1 second. It is, when I talk about Q dash, it is, in fact it is double dash. Okay, Q dash is basically heat flux, which is Q per unit area. This is watt per meter square. Q dot generation could be generation, could be anything, but this is Q per unit length, which is watt per meter. Okay, is it clear? So these terms you must be aware. Okay, so this is giving you Q double dash per unit length 5 watt per meter. Watt per meter. ठीक है, Sean, is it clear? It's not capital Q. It is capital Q per unit length. Okay. Chalo. The temperature of the surface of the wire is 75. So here T wall or T surface is 75 degrees Celsius. Now it is placed in air. Whatever air is flowing here, it has a temperature of T infinity 25 degrees Celsius. Okay. Now, when the wire is coated with the PVC of thickness 1 millimeter, now what we are doing? We are coating this wire. For example, this was my original wire. This was my original wire, and heat generation will remain same. Heat generation will, because whatever is happening, we are doing from outside. Okay. Now what we are doing? We are insulating it with a wire coated PVC. Okay. PVC material, which is kind of plastic. You see, you have PVC pipes. So now I have put a insulation here, PVC pipe. Okay. The temperature, now when the wire is coated, now this is your coating of PVC. And the thickness, now the thickness here is, thickness of this is 1 millimeter. Also in the question they have given you that the radius of this wire is 1 millimeter. Here it is given. Okay. Now you need to understand the question first. Okay, then only you will be able to solve this. Now, because of this coating, the surface of the wire reduces to 55. Surface of the wire, not after insulation. This surface again, this wall surface is reduced to 55 degree Celsius. Assume that the heat generation rate from the wire and the convective heat transfer coefficient will remain same. Okay, so heat generation is same, and the T infinity is 25 degrees Celsius, and heat transfer coefficient is also same. Okay, for both uninsulated and coated wire, the thermal conductivity of the PVC, I need to find out what is the thermal conductivity of this insulating material, which is PVC. This is what I need to find out. Okay, chalo. Let me take the first case. First case, uninsulated. Uninsulated. Okay, so how do I draw my resistance here? So what is happening? Look, whatever heat is generated, it will go out. Okay, and when it will go out, there will be some resistance. What is the resistance? If it is 25 degrees Celsius, it is 75, it is 25. So tell me what resistance is there. What resistance is this? Tell me very quickly. Which resistance will be here? Conduction, convection, which one will be here? Why conduction? Yes, Sahil, that is true. Look, at the surface, outer surface temperature is 75. So we are talking about this resistance. It is going out. Yes, that is correct. Shruti, is it clear why we are taking convection? Conduction, if we talk about, we will talk about inside the surface. But we are talking about temperatures at the wall and the air. So it is outside. Shikhar, is it clear why we are taking convection? So it will be 1 upon h into area. 1 upon h into area. Okay. Now, because we need to maintain this temperature 75 degrees Celsius continuously, steady state. So whatever, and how you will be able to maintain the 75 degrees Celsius? Whatever heat is generated, whatever Q is generated, it must be taken away by the air. It must be taken away by the air. Look, if more heat is generating and due to convection less heat is taken away, then what will happen? Surface temperature will rise. If less heat is generated and you have a very cold fluid, then the surface temperature will go down. But you do not want that. You want that steady state temperature will remain same at the outer surface. So that's why you need to be stick to this condition. Okay, ठीक है. So what is the heat generated? What is the heat generated? It is Q dot double dash into L. Q dot from this formula, okay, is equals to convection. Convection we all know. Either I can write it in terms of temperature, T wall minus T infinity upon 1 upon HA. Either I can write it like this, or I can simply write it HA T wall minus T infinity. Whichever way I want to write, I can write that. Okay. Now, this is 5 into L. H, I do not know. H. Into area is 2 pi RL. TW is 75 and T infinity is 25. Okay. From here, you can calculate H. From here, you can calculate H. Tell me very quickly how much is S. R is already given. R is 1 millimeter, so 0.001 meter. Tell me very quickly. Yes, Sahil, that is correct. Very nice. Sean, Shruti, what do you say? I'm sorry. Catch up, okay? Catch up with the speed. Please try to solve as quickly as possible. At least, okay, there are 4 or 5 people, but at least compete between these people, okay? Try to solve as early as possible. Whoever writes the answer first will win in this game, okay? Sean, Shruti, Shikhar, I'm saying this to everyone, okay? Try to write the question answer as quickly as possible. Yes, that is true. Now we got H. Okay, and that H is also same in this second condition. Because in the question they have given us what they have given. The temperature of this, assume that the heat generation rate and the wire and the convective heat transfer coefficient are same for both the case. Now let us take the second case, because I need to find out conductivity. So case 2. Now we have insulated. We have insulated our wire with a PVC pipe. Okay. Now what will I do? Look, again, whatever is here happening. So Q, with whatever heat is generated, must go out. It will go out, Q loss. Okay. Now what is the resistance here? Tell me. If I draw a resistance here if I draw this resistance, so this is 55 degrees Celsius and this is 25 degrees Celsius. So tell me what is R1 and what is R2? Which resistance is R1? Conduction, convection. Conduction, first conduction, second convection. Very nice. Anyone who has a problem with this? Anyone who has some doubt in this? Okay, very nice. Okay, so we all know what is the resistance in conduction. If you have forgotten what is the resistance or conduction resistance in cylinder, then you are in problem. Okay, we all know how to calculate conduction resistance in a cylinder. Ln R2 by R1 2 pi KL, and convection resistance is H into area, which is again 2 pi RL. Yes, very nice, Sahil. Ln R2 by R1 2 pi KL. Very nice. So by writing this, you see, Sahil, what did Sahil do just now? He has revised itself. Okay, so very nice. K is equals to 0.11. Very good. Very nice. Okay, so now I will do. So this is the heat loss. Because of this resistance, the same heat will go out. Okay, very nice. So now whatever Q is generated, so this is Q double dash into L is equals to Q loss. Okay, so let me write Q loss in a different way. What? In the thermal circuit way. What? T1 minus T infinity T1 dash upon R1 plus R2. Okay, chalo. This is 5 into L is equals to, now in the second case it is 55, it is 25, and ln R2 by R1 2 pi KL plus 1 upon H into 2 pi RL. Now look, L is same. L is same. So L can, you can take out, you can take on the numerator and it will get cancelled. It will get cancelled. Okay. Now what is R2? Look, R1 is 1 millimeter. Now you have added the 1 millimeter thickness. So it is R1 plus thickness. So it is 2 millimeter. 2 millimeter. Okay. So now you know R2, you know R1, you and 2 pi. Okay. So everything you know, now you can calculate K. Now tell me if anyone has any problem by calculating K. Very quickly solve it yourself. I don't want repeated answer. Solve it yourself. Write down if you have solved it. Write the answer in the comment box. Only if you have solved it. Only if you have solved this. Very quickly. So this is K of PVC. K of PVC. Tell me very quickly what is the answer. Now you can solve it easily. Don't. There is no problem. Are you solving this? At least tell me you are solving this. H is 15.9. Okay. Very quickly tell me what is the answer. I'm sorry, this is not K. This is 5. Fifteen point nine 2 pi R, 2 pi R, yes. And what is this R? R2, yes. Very nice. Very good. Outer area you will take. Outer area you are going to take. So into, yes. Have you solved this? I'm waiting for you guys here. Shruti, Shikhar, Sean. Okay, chalo. Somewhere I did mistake. Chalo, koi nahi. K you will get 0.11 and the unit is watt per meter Kelvin. Chalo. Shruti, are you getting the right answer? Shikhar, are you able to solve it? Are you getting the right answer? 0.116. I think it is correct. It's very close, so I am hoping it is correct. Because they usually ask you to do it, up to 2 decimal places, or they are asking 3 decimal places. Okay, okay. So yes, so I hope that is correct. Are you, Sahil? Did you get the same 0.116? Usually they ask you to up to 2 decimal places. Okay, in this question it is an exception. 1102. Okay, okay. Actually, the thing is, it is a very small number. It is a very small number. So you people are getting very different answer. If you like, very honestly, if you ask me, you are getting very different answer. If it is a big number, for example, if it is 100, then this much difference does not make a big difference. Okay, so okay. I don't know. Just try to solve this. Okay, you should get similar answers. No, I have actually put it directly. I've taken it everything on the one side, and then I have taken 5 on the other side. So you can further solve it. Okay. But this much, in this very small value, this much difference should not come. Okay. Another recommendation is ki, if in the calculation part, please do not round off figures again and again and again. Because if you are rounding off your answers again and again, for example, in 1 or 2 steps you have rounded off certain figures, like 2 or 3 times, then your answer will differ. Okay, so try to put everything all together in the calculator. Okay, or if you are rounding off, then do not round off until 3 or 4 decimal places. Okay, so that you will get a much closer correct answer. Okay, if you keep rounding off your values, then your answer will deviate from the actual answer a lot. Okay, that's what it is happening. Chalo, let us move on to the next question. Next question. This question: what is happening? 3 slabs are joined together. The last question is clear. Everyone, is the last question clear? Concept is clear or not? What we did is clear. Okay, very nice. Chalo. Now, GATE 2019 2-mark question. 3 slabs are joined together as shown in figure. There is no thermal contact resistance at the interface. I already told you what is thermal contact resistance. You see, I say that if if there is T1 and there is T2 and there is T3. Okay, so it will going to vary from T1 to T2 and then T2 to T3. But yeah, due to small air. So what happens is, sometimes, again, let me tell you one more time. I did not cover this concept in there, but let me cover it quickly here. Okay. So what happens, for example, you have a composite slab. Okay. Now here temperature is T1, here temperature is T2, here temperature is T3. Now how the temperature is varying? Like this: T1 to T2 and then T2 to T3. Now there is no temperature drop at the interface. Now this will only happen if there is no contact resistance. If there is a contact resistance, then what will happen? There will be some resistances here, and there will be a, because of that resistance, there will be a drop in temperature at the interface. Now how will you show that? You can show it like this: T1 to T2, then T2 to, this is T2, this is T1, and then because of contact resistance, there is a drop in temperature, and then it is T3, like this. Now why this why this contact resistance comes in? You see, first of all, you see, if this is the interface, these are two bodies. Now there will be some roughness here. There will be some roughness here, and also here, so there will be some roughness on the both the sides. Now because of this roughness, the actual area for heat transfer is less than the geometrical area. Now we all know all the heat transfer by हमने in the Fourier's law we have studied it is proportional to area and temperature gradient. Now if the area is less, so heat transfer will also be less, so the temperature drop will happen. Now This is the first reason. What is the second reason? Now, because there are voids, what will happen? Air will enter into this. Air will enter into this voids. Now, now thermal conductivity of air is less than thermal conductivity of the solid body. Solid body. And because thermal conductivity is less, again, less heat transfer will happen. And that is the reason, if these two conditions are significant, then the contact resistance will be significant. Is it clear? The concept of contact resistance is clear or not? Okay, everyone, I want answer from everyone. Sahil, once again. Okay, I have very clearly told you. I just wanted to focus on the question. Chalo, theek hai, I'll tell you one more time. So I'll tell you on this diagram only. Okay, so what happens? Look, if the contact between two solid bodies is perfect, okay, there is very less surface roughness. The contact is perfect, very perfectly they are joined together. So what will happen? There is no contact resistance, and there will not be any temperature drop. There will not be temperature drop at the interface. Now, because if there is some if there is some contact resistance here, then what will happen? The heat transfer will reduce, and because of that reduced heat transfer, the temperature drop will happen. So this case is basically with contact resistance. It is with contact resistance, and the upper case is without any contact resistance. Now, why this contact resistance happens? What is the reason of that contact resistance? That is what I am trying to tell you. Look, why this contact resistance things comes in. You see, look, if the contact between two bodies is not perfect, for example, these are two bodies. Okay, I am showing you in a macroscopic way. Otherwise, this much distance will not be there. You see, this is a joint between two bodies, body 1 and body 2. So we are showing it with one line, but this contact I am showing with two lines. Why? I am showing it in a macroscopic way. Now, the first body, you see that this first body will have some surface voids here, like this. Some surface roughness will be there. You cannot get a smooth surface. It is not possible by any machining process. Now, for body B also, you will have some surface roughness. Okay, now look, this is your geometrical area. This is your geometrical area. If this geometrical area and this geometrical area is joined together, so area for heat transfer is more. Okay, so if it is perfectly connected together, so a good heat transfer will happen. There is no contact resistance. But because of this void, so what has happened? Your actual contact area, which are in contact, is less than your geometrical area. In the body, inside the body, that area is more, geometric area. So because area is less, and we already know that Q conduction is proportional to area as well, and temperature gradient. Okay, now because area is reduced, so heat transfer will also reduced, and therefore there will be a temperature drop here. There will be a temperature drop that will happen here. Okay, now what is the second reason? Now, in these voids, air will get filled. In these voids, air and gases can get filled. Okay, now because of these gases, we already know if two solid bodies are connected together. Okay, so conductivity of gas is much less than conductivity of solid. So if two solid bodies are connected together, so it will have much higher conduction resistances. But if there is a gap between these two bodies and it is filled by a gas, then because conductivity is less, so again, because Qx is equal to K as well, Ka dt by dt. So if K is less, heat transfer is less. Again, because of this, there will be a temperature drop. So because of these two reasons, contact resistance arises. If these two parameters are significant, you cannot say that your contact resistance is negligible. Is it clear? Now is it clear? Okay, chalo. So I have not covered this earlier, but anyway, chalo, theek hai, now we have covered, although it is
Hello,
not a
sir.
very important concept, but in every question you will see there is no contact resistance, there is no contact resistance. So chalo, I have covered it.
Hello, sir.
Yeah, but just 1 second. Yes, tell me.
So only one thing here. Then after understanding the concept, so directly what we can do, we can directly use the convective heat transfer at the first and the last phase, and through this we'll get the answer, I guess.
Tell me one more time.
So we can use the convection heat transfer, which will be happening in the first phase and then the last phase, second phase.
No, yeah. Look, convection heat transfer will not work here. Why? I'll tell you why. Look, these voids, no, these are very small voids, right?
Okay.
So whenever air or any gas will trapped here, it will not move much, right?
No, so that's what. At the first phase where we have the T1, at that surface we'll calculate the convection heat transfer because there is a T1 and also there is a 30 degrees centigrade. Also that air is like how the air is flowing. So at that phase and in the second phase also we'll calculate the same respect, and that will be the
No.
total heat.
1 second, 1 second. You are talking
Okay.
about the question or the contact resistance concept?
Yes, sir.
Hmm? Are you talking about the
Sorry,
question
sir.
or you are talking? 1 second. Are you able to listen to me? Is my audio clear?
Yes, sir. It's clear now. Yes, sir. Please.
So I am asking, are you talking about the question that we are going to discuss or about the contact resistance concept?
Sir, about the resistance concept only.
Okay. Now tell me what you are trying to say. That we have 30 degrees Celsius here, right? That is what you are saying.
Yes, sir. Yes,
We
sir.
have 30-degree here. So what are you saying now?
So, sir, what we can do, like at 30 degrees centigrade, what will be the convective heat transfer at that phase,
Hmm. Mm-hmm.
at left extreme phase, and what will be the convective heat transfer at the right phase at T2,
At
and that will
T2,
be the net. That will be equal to the internal heat generation. What we have in total.
Are to Baba, that is about the question, no? That is not about the thermal contact resistance, no. Abhi to, I just told you what is contact resistance. Abhi to I have not even started the question. I really do not, I mean, I'm really sorry, but you are saying that whatever heat is generated, है ना, that you can calculate what? What do you want to calculate? T2. That is what, are you saying this?
Oh no, sir. I'll just read this one again because I was trying to apply something else. I'll try to read it one more time and I'll look for it.
No,
Like
no,
if I
look,
have
look, look.
this, yeah.
Sahil, I have not even discussed the question yet, so I do not know what the question is saying. Okay, because this line was written here, so I am trying to tell you that the contact resistance concept. Also, there is one more thing I would like to tell you that if you are saying that whatever air is there, for example, inside the voids, right? So you are saying that you can calculate heat transfer instead of conductivity, you can calculate heat transfer by H. Are you saying that? Were you saying that or you were saying something else? So you were saying we can calculate H from here. Eh? So, okay. So now let me explain you one thing. Look, I have told you H is basically, it is not the property of any fluid. Okay. If you are saying, okay, I don't know what fluid is here, I will read the question later. But let us say this is air. Okay, and this is your H, 100 watt per meter square. ठीक है, it's okay. But at outer side, velocity will be more, right? Here we have voids, and the voids are very small. So if air enters into those voids, it will not move with this velocity. It will move with much less velocity. So this H will also be very less. I told you H is a function of velocity, characteristic dimension, okay, density, Cp, viscosity, conductivity, so many things, isn't it? So you cannot calculate H, you cannot take this H and calculate heat transfer. Okay, so you cannot calculate heat transfer here, and anyway the velocity will be almost zero. If the air is trapped in these voids, the velocity is almost zero. So if the velocity is almost zero, it will have very, very low heat transfer anyway. Okay, higher the velocity, higher will be heat transfer coefficient. Okay, clear? Question, so I am not even, I mean, we have not even read, so I don't know what you were saying about question. But if you were saying this, so I think I have answered your question. You cannot take this h to calculate that heat transfer. Okay, how much heat transfer is happening. Then you have to go into deep into books and see ki bhai, how you can calculate h. First of all, you have to calculate h. Okay, chalo. Let me. So much discussion has happened. Now let's read the question. Any doubt? Anyone? Do you have any other question? Shruti, Sean, Shikhar, Sridev is also there. Anyone? Any question? Chalo. Okay. Heat transfer coefficient is always defined experimentally. It is always as soon as you change the fluid, heat transfer coefficient will change. As soon as you change the velocity, heat transfer will change. As soon as you change the position orientation of the object, for example, an object is horizontally placed, then heat transfer coefficient under all the other parameters, if all you see, I told you this, f velocity, this rho cp mu k. So if all other parameters are constant, still if you have a horizontal body, if you have this body, the heat transfer coefficient will be different. Yes, characteristic dimension. Okay, so you see here the characteristic dimension is different, and in here characteristic dimension is different. So again you cannot calculate. So there are so many reasons. Okay, chalo. It's not as simple as we think. So chalo, theek hai. Let us move on. That's why they are always saying कि भाई take contact resistance as negligible. ठीक है, chalo. Let us read the question slowly and then we'll start the question. Chalo. Now we have joined three slabs and contact resistance is 0. Now the center slab experiences a non-uniform internal heat generation with an average value of 10,000 watt per meter cube. Very quickly tell me what is this 10,000 watt per meter cube? Capital Q, small q. Yes, this is first body, this is second body, and this is third body. In the second body, there is some Q generation. How much? 10,000 watt per meter cube. While the left and right slabs have no internal heat generation. In first and third, there is no internal heat generation. All slabs have thickness. So L1, L2, and L3 are same. Okay. And each slab conductivity is also same. Conductivity of each slab is also same. How much? 5 watt per meter Kelvin. Same conductivity everywhere. Now the two extreme faces are exposed to fluid with heat transfer coefficient 100 watt per meter square Kelvin and bulk temperature 30 degrees Celsius. So both sides, you see both sides, T infinity out is 30 degree, T infinity I is 30 degree. HI is 100 watt per meter square, H out is 100 watt per meter square. Okay. Now the heat transfer in the slabs is assumed to be one dimensional and steady. Okay, one dimensional steady, and all the bulk properties are constant. It is steady. I am saying that T1 is given as 100. And because it is non-uniform heat transfer, you see non-uniform heat transfer. Okay, so T2 will be different. T2 will not be equal to T1. I need to find out T2. I need to find out T2. T1 is given. Okay, but it is steady. Steady means what? Whether it is T1 on the left hand, whether it is T2 on the right hand, but it will remain constant with respect to time. It will remain constant. It will not change. It will remain constant with respect to time. Okay. So if the left extreme phase is T1 is measured to be 100 degrees Celsius, the right extreme phase of temperature T2 I need to calculate. I need to calculate T2. Okay. Is the question clear? Is the question clear? I need to find out T2. Okay, now let's try to understand that. Now what is happening here, you see. Look, here, let's say we have an electrical rod or something, whatever a heat generation source is there. Okay, so here we have Q generation that is happening. Okay, now whatever heat is generated here, now heat is not generating only in the center. heat is generated everywhere, okay, in this whole slab. Now whatever is generated, it will be conducted and then convected. So let's say it is Q dot conduction 1, and it will be conducted here as well. Not equal, I am not saying they are equal. Q dot conduction 2, okay, and then it is steady state, it is steady state. So Q dot convection will also happen, and it will be equal to Q dot conduction 1, and here also Q dot convection will happen too, and it will be equal to this. Okay, so do you, if I say look, if I say Q dot generation, whatever heat is generated, it is equals to Q dot conduction 1 plus Q dot conduction 2. Conduction 2. Do you have any problem with this? If I say this, because it is steady state. So whatever heat is generated, nothing can be stored. Nothing can be stored in the body. Steady state means the temperature will not change with respect to time, either inside the body or outside the body. If more heat is generated, then the temperature inside the body will change, or outside will also change. But it cannot happen because steady state is there. Temperature anywhere is not a function of time. If I will remove less heat, heat generation is more, then the temperature will change with time. After 5 minutes, the body will be more hotter, temperature will be higher. Okay, so anyone has a problem with my first statement? No, very nice. So it is clear, I hope. Okay, chalo. Now let us take left side. Let us take left side. So can I say whatever heat is conducted at this border, if I am talking about this border, I am talking about this border. Okay, I am talking about, and it is steady state. It is steady state. Steady state. So can I say Q dot conducted 1 is equals to Q dot convection 1 at this border, at this left side border? Yes, very nice. So can I calculate Q dot conduction 1 is equals to H A T1 minus T infinity I. Right? I can do that. Now let us see one more thing. I have given this, they have given me this. Okay, so they have given me Q dot generation is equals to 10,000 watt per meter cube. That means Q dot generation is equals to 10,000 into volume, right? Now it is what? So 10,000 into area into L. What is the L? Is this L is this L1, L2, L3, which is same. What is area? This area. Okay, so let me take, this is 1 and 1 meter. So area is 1 meter square. So 10,000 into 1 meter square into 1 meter. So it is, I will everywhere I'll take 1 meter square area itself. Okay, it means I am calculating per unit area. Okay, so this is what Q dot generation is 10,000 watt. Okay, now, okay, so Q dot generation, this is given to me. It is given to me. Okay, now I can calculate H. H is given 100 watt per meter square Kelvin. Area is again 1 meter square. T1 is 100 and this is 30. So it's very simple. 17 to 100, 7,000 watts. Q dot conduction 1. Okay. Now, if I know that this is 10,000, I know that this is 10,000 watts. So if I put this in this equation, can I say Q dot conduction 2 is equals to 3,000 watts, right? Anyone has a problem? Yes, that is correct. Sahil is very correct. It is 60 degrees Celsius. Okay, very nice. And it is also equal to, at this surface, now I am talking about this surface, bhaiya. So it is also equal to Q dot convection 2, okay, which is equals to H area T2 minus T infinity. Okay, so this is 3,000. H is again 100. Area is again 1. T2 I do not know. Minus T infinity is 30 degrees Celsius. Yes, I know that we can cancel it out. That's why I am keeping it 1. Okay. You can actually put here area. You can put area here. Okay. And then you can cancel. But again, we are carrying one term with us for a longer period. It does not make much sense. Okay. We can cancel that. I know that we can cancel. But I have assumed per unit area. So I have taken it 1. Okay. Chalo. So here you can calculate very easily that T2 is equals to 60 degree Celsius. Is it clear? Sean, Shruti, Shridev, Shahil, Sikhar. Okay, very nice, very nice. Let us move on to the next question. Okay. Now, a cylindrical rod of length L, diameter L. Okay, let me draw this. What do we have? We have a rod. We have a rod. Okay, it has length L, diameter is D, and they are saying length is much greater than D, and the thermal conductivity is K1. Okay, now it is joined with another rod of identical dimensions. Now I have joined it with another rod of similar dimensions, means length is again L, length is again L, and diameter is again D. Okay, so its conductivity is K2. Now they are saying to form a composite cylindrical rod of 2L. Okay, the heat transfer in radial direction and contact resistance is negligible. So at this point, contact resistance is negligible, and they are saying heat transfer is not happening in R direction. Heat transfer is not happening in radial direction. Okay, it is happening in axial direction. It is happening in this axial direction. Okay, it is happening in, let's say, X direction. Okay, the effective thermal conductivity of the composite slab. So I need to find out K equivalent. K equivalent I need to find out. So what can I do? I can take a equivalent slab here which has a length 2L. I can take 2L and it has a equivalent thermal conductivity K. Diameter is D itself, no problem. Diameter is D itself. Okay. So now you see these rods. Is it a parallel? It is a parallel connection or a series connection? Can you tell me, is it a parallel or series connection? Everyone. Sahil, Sean says series. Sahil says series. Shruti, series. Sikhar and Shridev. What do you think? What are your thoughts about it? Okay, that is series itself. Yeah, series. Okay, and we all know how do you calculate resistance? R equivalent is equals to R1 plus R2. Okay, now what is R equivalent? R equivalent is L upon Ka. Okay, so for this equivalent rod we have 2L and K equivalent. Okay, area will remain same. Area will remain same. And now R1 is the first rod. R1 is L upon K1A plus L upon K2A. L upon K2A. Okay, chalo. So L will get cancelled. Area will get cancelled, and you will get K equivalent. K equivalent. No, Sahil, I don't think that is correct. If you calculate this, it is K equivalent is equals to 2. Okay, just 1 second. Let me do this. It is 2 upon K equivalent, 1 upon K1 plus 1 upon K2, and this will be equal to K1 plus K2 by K1 K2, and K equivalent is equals to 2 K1 K2 upon K1 plus K2. Okay, so the answer is A. Is it clear? Is it clear? Okay, Sean Shruti says yes. Do you have any doubt in this question? Any doubt in this question? Sahil, any doubt? Shikhar, Sridev? No. Okay. So tell me one thing. When we studied cylinder, you don't have any doubt, but I have some doubt. Okay. When I told you cylinder, so what was the resistance in a cylinder? If the conduction is happening, what was the resistance in a cylinder? Ln R2 by R1 2 pi k L. Isn't it? Yes. So why I have not used this here? Why I am not? I have used, this is for rectangular, Baba. This is for plane slab, rectangular resistance, isn't it? For plane slab is equals to L upon Ka. So why? Yes, Sean is correct. Very nice. I'm very happy that you know the reason. Sahil, do you know the reason? Look, when we calculated by using this formula, I was saying heat transfer is happening in radial direction. Okay, so when heat transfer, then the question will say radial direction. You will use what? 2 pi kl T1 minus T2 ln R2 by R1. When they say in axial direction, so you can simply use Ka T1 minus T2 by L. Okay, clear? But you must have this doubt. Why, sir? Why are we using this resistance here? Because cylindrical resistance, we studied something else. Okay, is it clear now? Okay, very nice. Let me just take some water and then we will start again. Chalo, let us move on to the next question. So, now what is happening in it is GATE 2021 mark question. Okay. Now, in a furnace, the inner and outer sides of brick wall, okay, inner and outer side of brick wall, K1, 2.5. So, thermal conductivity of this brick wall is 2.5. They are maintained at 1100 and 700. So, this side is 1100, this side 700, as shown in figure. Now, on the one side, we have covered it with the insulating material of thermal conductivity K2. So, this has a thermal conductivity K2. It is an insulating material. It is an insulating material. Now the thickness L2 is basically 4 times L. The thickness of insulation is 1/4 of the thickness of the brick wall. So L2 is L1 by 4. L2 is L1 by 4. The outer surface of the insulation is at 200. This is 200. The heat flux through the composite wall is 2500 watt per meter square. Now what is this? This is Q dash, capital Q per unit area. So this is 2500 watt per meter square. Okay, what area? This area. Whatever the area is, it is same, right? This same, this area. Okay, it is same from one side, from this side, 1, 2, 3. It is same only. Okay, so it is 25. So heat transfer is happening 2500 watt per meter square. Now I need to determine K2. I need to determine K2. Before I do anything, let us draw a thermal resistance here, thermal circuit. Okay, now this is what? This is here temperature is T1, here temperature is T2, and here temperature is T3. Okay, now let's say this is R1, this is R2. Now it is what? L1 upon K1A, this L2 upon K2A. Okay, now by Fourier's law, I can say whatever heat transfer is happening, it will be equal to T1 minus T2 upon R1. It will be equal to T2 minus T3 by R2. Or I can say T1 minus T3 R1 by R2. I am just telling you this. I don't need to write everything. In exam, you don't have to write everything. I am just telling you that I can start with this equation as well. Okay, I can start with this equation as well, and I can find out something. What I can, I will not find out anything. Actually, everything is known to me. Okay, and what can I do? I can take this and this equation as well. But I need to find out what is the most convenient equation to use. Okay, the most you can start with anything. You will be able to solve it, no problem. Whatever you equation you will use, you will be able to solve this because only one unknown is there in the whole equation. But I need to find out what is the most convenient equation relationship. Now this is the most convenient relationship. Why? Only one unknown, nothing much to do. Upon R1 is L1 upon K1. K1 is 2.5 and area. T2 is again 700 minus 200 upon L2. L2 is how much? L1 by 4 K2 area. L1 and L1 will get cancelled. Area and area will get cancelled. And you can find out K2 from here. K2 from here. Tell me very quickly how much is K2? How much is K2? It is 0.5. Okay. Very nice, Sahil. Shruti, Sean, are you able to solve this? Shikhar and Shridev. Is it clear? Very simple question. It is 1 mark question, gate 2020. Very simple. It should not take you more than 30 seconds to solve this type of question. More than 30 seconds. Sir, 30 seconds, you start with this equation itself. You will not write any shit there, anything there. Okay. You start with this equation and as simple as that. Nothing else. Okay, okay. Yes, yes. Yeah. During practice, again, write and write every time, write the formula. Okay. So that you will, I'm saying this, give you always prepare for the worst. Always prepare for the worst and hope for the best. Okay. So basically, during preparation, you have to write the formula, you have to draw the diagram. You do not need to draw this diagram as well. Okay, so during preparation, yes, you need to write the diagram. I'm sorry, you need to write the formulas, draw the diagrams. Okay, write as many formulas again and again and again until it is imprinted on your mind. Okay, so write all the formulas again and again so that in exam you do not need to write the formula. Just write the equation, write the value, solve it, and give the answer. Not more than only two steps, and not more than 30 seconds. Not more than 30 seconds. Chalo, let us move on. Next question. Okay, tell me this. Now a plain slab of thickness L and thermal conductivity K. K is 2.5 and L is 20. Okay, is heated with a fluid on one side. Here it is heated with one fluid at one side, and on the other side the temperature is maintained of 25 degrees Celsius. Okay, now the fluid that is heating the slab, it is 45 degrees Celsius, and the surface heat transfer coefficient H is 10 watt per meter square Kelvin. Okay, the steady state temperature TP I need to find out. This I need to find out, which is exposed to the fluid. Very simple, very simple. Okay, so you need to draw a resistance here. You need to draw another resistance here. Okay, so what is this, bhaiya? This is TW, this is TP, and this is TQ. Now tell me, what is this R1? Which resistance is R1? Conduction or convection? Conduction or convection? Convection. Very nice. What is R2? 1 upon H area. What is area? This is the area. This is the area. Length, this width into height, which will remain same for conduction and convection. Okay. Now what is this R2? R2 is what? Conduction or convection? Conduction. Very nice. So this is L upon Ka. Now area is same for conduction and convection. Both area will remain same for conduction and convection. I need to find out Tp. Again, I can write Q and everything. The same equation I can write here, like I wrote here, but I do not need all that. What will I can only solve it from here. Why? By TW minus TP 1 upon HA is equals to TP minus TQ upon L upon Ka. Now area is same for conduction and convection, so it will get cancelled. Everything else I know, but I need TP. I need TP here. So TW is 45 minus TP 1 upon it is 10. Okay, is equals to TP minus 25. L is how much? 20 centimeter. So 0.2 and conductivity is 2.5. And you only one unknown is there, and Sahil has already solved it. Very nice. Sean says 45. No, Sean, 45 is not the answer. Is it the answer that you were saying? No, it is not the answer. TP is 33.89 degrees Celsius. You see, this is a 2-mark question. This is a 2-mark question. You see, as simple, and it is not very old question, 2018 question itself. Okay. So if you know the concept, then GATE exam is not at, I'll tell you what, you see 60% of the paper is actually easy. Okay, actually not 60%, around 30 to 40% paper is actually easy, like you can easily qualify, no problem. If you have done anything, you can easily qualify. If you have just gone over the books and just written all the formulas, you do not know anything about the concept, just written all the formulas and understood that this formula can be used in this particular situation, still you will be able to score 30 to 40% mark, as simple as that. Then around, you see, around 30 marks question, 30 to 40 marks question is very easy. Then 20 to 30%, in fact 20 to 40% is intermediate. Okay, little bit understanding you would be required, and then last 20 to 30% is basically hard. Okay, so going over 60 marks, getting more than 60 marks is basically difficult, but less than 60 is not very difficult. Okay, so do not stress yourself too much. Do not stress yourself कि यार इतना करना है, वो करना है, ये करना है, यार कुछ नहीं करना, आराम से पढ़ो, सब हो जाएगा. Okay, so going more than 60-65 marks is basically difficult. Okay, but again it is not impossible. If you try hard, of course you will get it, no problem. Chalo, let us move on. Is it clear? Very easy question. Let's move on. Chalo, theek hai. Yes. Next question. Steady one-dimensional heat conduction takes place across phase 1 and 3 of a composite slab. Again, 2016 1-mark question. 2016 1-mark question. Slab A and slab B in perfect contact. Again, perfect. These are the word to tell you that there is no contact resistance. No contact resistance. As shown in figure. Ka is given, Kb is given. Okay. Using the data, calculate interface temperature, calculate T2. T1 is given. Simple, very simple. Bhaiya, isse simple what? Nothing can be simpler than this. Okay. This is 130 degrees Celsius. T2 I need to calculate. T3 is equals to 30. Now tell me how is this hard? Now tell me how is this question hard? Nothing is there. L upon Kaa and L2, L1, L2, Kb. Area is same again, same area is there. What is the issue? No issue. Cancel the area, same area is there. Calculate how much is T2. Very quickly tell me. I'm not going to write anything. Actually, I will write something, but you tell me what is the answer before I solve it. T1 minus T2 upon R1. T2 minus T3 upon R2. Okay. Now 130. Similar like the last question itself. L1 upon Kaa. T2 minus 30 L2 upon KB B. I'm sorry, KB B. Area and area will get cancelled. Okay. and you can put the values. 130 minus T2, L1 is 0.1. This is 20. T2 minus 30, L2 is 0.3 and 100. You can find out T2 very easily, and Sahil has calculated it correctly. T2 is equals to 67.5 degrees Celsius. Very nice. Very nice. Sean has also calculated. Very nice. Shridev, have you calculated? Shikhar, Sean, Shruti, have you calculated? Look, if you find these questions easy, that means you are at an appropriate level. Okay, you are at the appropriate level. It is not, yes, it is in degrees Celsius. If you, because you are putting all the temperatures in degrees Celsius, that means you will get your answer in degrees Celsius. Okay. And what was I saying? If you are finding these questions easy, that means you have reached the level. But you need to prepare for the worst exam that can happen. So you need to practice more and more different type of questions. But if you are finding these questions hard, if you are not able to remember the formulas, if you're not able to understand the concept, that means you have not revised the concept. Okay, if you're not able to understand what I am doing, then you have not revised the concept. Okay, if you understand the concept but you are not able to remember the formulas, that means you need revision. Okay, third, if you are finding these questions hard, then you need more practice. If you are finding these questions average or fine, or you are comfortable with them, that means your concept is covered, your revision is done, your only thing you need more and more and more practice. That's all. Okay, there's no substitute to practice. Chalo, let us move on. Yes, I'll leave you early today. I'll finish the class by 10:30, 35. I hope. And I'll leave you early. Chalo. A plastic sleeve of outer radius R not 1 millimeter covers a wire. So we have a look, we have a wire. We have a wire of radius 0.5 millimeter. Okay. Now what I have done, I have covered it. I have covered it with a plastic sleeve. With a plastic sleeve. And the thickness is 1 millimeter. Thickness is 1 millimeter. Okay. Outer radius is, now the outer radius of this is, no, total is 1 millimeter. Okay, not the thickness. Outer radius it is telling me, not the thickness. Total is 1 millimeter. Okay. It contains electrical current, thermal conductivity of the plastic. Thermal conductivity of this plastic, which is basically acting as an insulation, is 0.15 watt per meter Kelvin. The heat transfer coefficient of the outer surface here is 25 watt per meter square Kelvin. Now, due to addition of plastic cover, the heat transfer from the wire to the ambient will increase, remain same. So whenever you see this type of question, always calculate critical radius. Yes, very nice. Critical radius. How do I calculate critical radius? What is critical radius for a cylinder? What is critical radius for a cylinder? K by H. What is the critical radius for a sphere? What is critical radius for a sphere? 2K by H. Very nice. Everyone should answer, yeah. Please revise your concept with me. That's why I know I can directly write and move on. Okay. I want you to write your answers in the comment box so that at least you will get one more revision. Okay. Shruti, Shridev, Shikhar, kindly write, yeah. People, why are you not writing? It's for your benefit. Okay. It's not for my benefit. I can just give you the formula and move on. I don't have any problem. Okay. Chalo. Let us see. Now, what is the critical radius? What is the critical radius? It is insulation is 0.15 and 25. Okay. So this is how much? This is 6 into 10 to the power minus 3 meter. And this is 6 millimeter. Okay. So you see, if you are taking just wire, then the radius is 0.5 millimeter. Even if you have added this plastic sleeve, so now the outer radius is 1 millimeter. So outer radius of this sleeve, let me not write it here. I want to draw a diagram here. Okay. So outer radius of this sleeve is basically less than the critical radius. So, and we all know that if this is your Q and this is your radius, then the graph is something like this. Okay. Here it is, we find maximum heat transfer at RC. Okay. Here we have R less outer radius less than RC. Here we have outer radius greater than RC. Now, because my R naught is less than RC, for example, somewhere here is my RC. Okay. So if I increase my RC, my R naught, then I'll go this side. That means heat transfer will increase. It will reach to a maximum at RC and it will reduce after that. So first of all, it is going to increase. If the option will say it will increase, then and then become maximum and then decrease, then that will be the correct answer. Okay. But here there is no such option, so it will increase. That is the right option. Okay. Clear? So Q will increase. Chalo. Not more than 15 to 20 seconds. 20-second questions in question in gate. So you add more. No, that is what we are saying. Look, you are here. Let's say you are at 1 millimeter. Then you add. So when you add, the outer radius will increase. Plastic, then the current thickness. Are Baba, Sean, you add, no problem.
Hello, sir.
Tell me.
Like I really understand the last statement of the question. Like I got 6 mm. I know that if we increase above 6 mm, it will get reduced, and if we decrease below 6 mm, it will also decrease the transfer. But what is that line I said? The question asked, I didn't understand.
Okay, look, it is saying due to the addition of plastic. Okay, so you see the earlier outer radius was, let's say R01 was 0.5 millimeter. So for example, you were here R01. Then you added plastic sleeve. So you got 1 millimeter, right? So now let's say you have reached here R02, isn't it? Because you will increase in this direction, no radius. So now because you have come from 0. Yani ki R01, 1 second, let me choose black pen. Because you have gone to R01 to R02, just 1 second. You have gone from R01, your earlier radius was R01. Then you have added plastic sleeve. So they are asking, due to addition of plastic sleeve, what has happened to heat transfer? So because of addition of plastic sleeve, the radius has gone to R02. So your heat transfer has increased from Q1 to Q2. If you keep adding more and more and more, it will increase up to critical radius, and then it will reduce. Okay, clear? This is what it is asking. Key, when you have added the plastic sleeve, plastic cover, then what happened to the heat transfer? Okay, if for example R01 was 7 millimeter, okay, so that means you are already here. This is your R01. This is 7 millimeter. Now you have added your this plastic sleeve, and let's say it is 1 millimeter thickness. So it has gone to 8 millimeter. Now you have gone to here. So now what will happen? If you are on the other side, then it will reduce here. Okay, I hope it is clear. Yes, chalo. Next question. If a foam insulation is added to a 4 centimeter outer radius pipe, okay, this pipe is there. You have this pipe, outer radius pipe is there. Now you are adding foam insulation. This is your insulation, foam insulation. Okay, the critical radius of insulation they are asking. Critical radius of insulation. You need to tell me very quickly. It is a pipe. Pipe means cylindrical surface. RC, how much is RC? Tell me very quickly. Tell me very quickly how much is RC, critical radius of insulation. One watt in centimeter. 1 centimeter? No, that is not correct. Sean, speed is important, but accuracy is as much as important. I think you have taken the you have taken something. I don't know what you have taken, but something wrong you have done. Calculate it again. K of insulation upon H. 100 centimeters. No, Baba. How 100 centimeters, yaar? 100, yes, 5 centimeters. That is correct. Why? What mistake are you doing? Look, K of insulation you will take every time. I think you have taken K of pipe. Have you taken K of pipe? What did you do? Tell me what mistake you have done. Every time you have to take insulation conductivity and outer heat. Already taking answer from memory. Okay, you are telling answer by memory, huh? Why are you doing that?
Hello, sir. No,
Well,
sir. Like,
yes.
I am using that memory power of that memory option of calculator, and that was saved different value. So when I divided, I got
Achha.
100.
You divide by what? 400.
No. That answer had some value. I didn't like properly save that, so it came 100. I don't know what was that stored in that memory.
ओके ठीक है ओके चलो ठीक है डोंट डू दैट इन एग्जाम ओके चलो के इंसुलेशन इज व्हाट इज इंसुलेशन फॉर्म इज द इंसुलेशन 0.1 always take K insulation here and outside because you always increase the radius in outside radius you will whenever you would try to increase the thickness okay so you always increase the outside radius so H naught outside H you will take so which is 2 okay so this is 0.05 meter and it is 5 centimeter okay chalo let us move on next question a 10 millimeter dia it is 2 mark question gate 2015 2 mark a 10 millimeter dia electrical conductor is covered by an insulation of 2 millimeter thickness okay the conductivity of the insulation is this and the convection coefficient at the insulation surface is 10 addition of further insulation of the same thickness okay now look you have a conductor of 10 millimeter so let's say 5 millimeter is there then you have added some insulation you have already added some insulation of 2 millimeter thickness 2 millimeter so your total radius outer radius is 7 millimeter okay now it is asking addition of further insulation if you are adding further insulation then what will happen okay if you are adding further insulation that what will happen so same thing I need to find out critical radius K of insulation by H naught K of insulation is 0.08 and this is 10 so this is I think 8 millimeter okay it will 0.08 meter and then 8 millimeter okay so same you know the diagram that because R is less than R naught is less than RC so first heat transfer will increase then it will reach to Q maximum at R's critical radius and then heat transfer will start reducing so what is the answer increase heat loss to a maximum and then decrease the heat loss yes that is correct Shruti is it clear Shikhar is it clear chalo so you see it is a 2 mark question how much time it is going to take not more than 30 seconds ठीक है चलो next question so next question says a material P of thickness 1 millimeter एक P material है its thickness is 1 millimeter. Okay, it is sandwiched between two steel slabs. Their steel slabs are there. Okay, a heat flask 10 kilowatt per meter square. We are passing this heat flask is supplied to one of the steel slab as shown. Okay, the boundary temperature of the slabs are indicated in the figure. So here we have T1, here we have T2. Okay, assume thermal conductivity of the, so this K is equals to 10 of steel. They are saying steel, they are saying, so both are steel slabs, that's what they are 10. Considering one dimensional steady state heat conduction for the configuration. Steady state means same heat transfer is happening all through the body. Okay, the thermal conductivity of, now this Kp I need to find out. Kp I need to find out. Okay, so what can I do? Can I draw the resistance here? Yes, I can. Okay, now this is 500. This is T1, this is T2, let's say. This is T3, let's say. And this is 360 Kelvin. 360 Kelvin. Okay. Now this is my R1, this is my R2, this is my R3. Okay. Now how can I calculate R1? R1 is L upon K1A. This is L2 upon K2A. And this is L3 upon K3A. Very simple, isn't it? And we all know that from Fourier's equation, I can write. Look, now again, you can take any two circuits. You can take the whole circuit. You can take two circuits. You can take three circuits. But what do I need? I need this K2. I need this K2 or Kp. Okay. I have no problem with this T2. They are not asking T2. Okay, so if I take only this resistance, then first of all I need to find out T2 and T3, then I'll take this resistances. Okay, so I will not do that. What will I do? I'll do total Q is equals to T1 minus T2. Okay, this is T2 actually. Let's say this is T dash and T double dash, whatever you want to call it. Okay, and it will be R1 plus R2 plus R3 plus R4. Okay, so this is what you can do. Is it clear? Is it clear? Yes, that is 0.1. That is 0.1. Very nice. Okay, so will you be able to solve this? Will you be able to solve this? Do you want this question for homework? Do you want to try this? Okay, Sean. Yes. Okay. Chalo, this you can take for homework. I don't know. Let's say this is the last question. I think this is the last question. Okay. Okay, let's say one more question is there. Let us try this as well. I thought that was the last question, and then we will close the class. Okay. I have already taken, some extra time from you. So today I'll give some extra time so that I can take that time again from you whenever I have to cover a concept, because covering the concept is very important. I cannot compromise with concept. That is my, one thing that I cannot do. Okay. Numericals, look, I have covered mostly all the previous year that can come from this concept. Now it is up to you. Solve from workbook, solve from any source you would like, but try to solve all the questions. Utilize your time to solve the questions. Okay. So the more questions you solve, the more concept will, clarity will come. Okay. Chalo. Last question, very simple question. Consider one dimensional steady state heat conduction across a wall. This heat conduction is happening. This much heat is going. Okay. Of thickness 30. This thickness is 30 millimeter. And thermal conductivity is 15 watt. K is equals to 15. Now at X is equals to 0. Temperature is T1. Okay. On the other side of the wall, heat is removed. So it is TW. It is TW. Okay. Heat is removed from the wall by convection. Now here we have convection. So water temperature is there. Okay. Convection with a fluid. Some fluid is there. At this side of the wall, temperature is T2. At this side of the wall, temperature is T2. And heat transfer coefficient here, it is given 250 watt per meter square. Now what are they asking? I need T1. I do not care about T2. I need T1. I do not care about T2. I need temperature at x is equals to 0. Okay. So I can draw a resistance here. Bhaiya, this is my resistance. It is T1. It is T2. And it is TW. Okay. Now R1 and R2. R1 is, I hope you all know. Now I don't think I need to ask you. R1 is conduction resistance. It is L upon Ka. And R2 is convection resistance HA. Now area, conduction area is same only. Okay. Look, for conduction it is the perpendicular area. Or for convection it is the area of heat transfer. So anyway fluid is flowing over this area. No. So area is same for conduction and convection. Okay. So very simple. Now I can do what? I can do Q dot, whatever Q dot is going on in X direction will be equal to T1 minus TW upon R1 plus R2. Okay. I can also write T1 minus TW upon L upon Ka plus 1 upon HA. 1 upon HA. Okay. Now area is same. Look, I know area is same. What can I do? I can take area common. I can take area common here. I can take area common here. So right like this I can write. Okay. Now why not take this area here in the numerator? Let's take this in the numerator. So by the same way, I can write Q dot X by A is equals to T1 minus TW L upon K. Look, these steps is not required. These steps are not required. I'm just telling you so that what I am doing should be clear to you if you have any doubt. Okay. Now this is what is given to me. Q double dash is given to me. Okay. I said this is Q dash. Anyway, designation does not matter. What matters is what unit we are taking. So you should know whenever watt per meter square is there, it is capital Q upon area. When watt per meter is there, then it is Q per unit length. Okay. So when watt per meter cube is there, that means capital Q per unit volume is there. So this is important. Designation is not very important. What you are trying to say, you can designate by anything, no problem. There is no standard designation for it. Yes. Chalo. So this is given. This is how much? This is 1 into 10 to the power 5 is equals to T1 I need to calculate. TW is 25. Length is given 30 millimeter. So 0.3 K. K is how much? K is 15 plus 1 upon 250. 1 upon 250 and Sahil Sean has calculated. C. What is C, bhaiya? Where are the options C? Acha, degree Celsius. Okay, very nice. Very nice. Okay. So T1 you will get 625. You will solve this and you will get T1 is equals to 625 degrees Celsius. Very nice. Very nice. Okay. So you got one question for homework. Try to solve that question. Okay. Very simple question. There's nothing new that we are going to discuss there. Okay. I will share the PDF with you in the WhatsApp group. So now are you comfortable with the, I don't know if you have practiced earlier, but now what do you think? Like the concept, it is all, look, today I have solved all the gate questions. I have not made these questions myself. I have not brought the questions based on what I have taught you. Okay, I have brought the gate questions. So if you are able to solve gate questions means that our concept covered, that the concept that we have covered are, we are in the right direction. Okay. So tell me, Are you more comfortable? Are you more confident? Do you get more confidence in what you have studied or not when you are able to solve questions? First question I forgot that I will redo and check if the doubt comes. Sure. Ask. First question means generation. If you want to ask now, you can ask today, now itself. No problem. I have no problem with doubts, because if that is my, I mean, if you are having doubt, then my job is not done. Okay, tell me, what is the doubt? Actually, whatever we have done here, if you solve the derivation, no, you will know, you will remember this, no problem. Okay, this comes from derivation itself. This comes from derivation itself, and under these assumptions. So if you do that, you will remember that. It will come to your memory. Yeah, okay. Yeah, you should try. Okay, chalo. Tell me, are you more comfortable? Are you feeling more confident? Confidence in the concept that we have covered? Okay, चलो ठीक है. चलो तो फिर let's meet tomorrow. We will start. What do we start tomorrow? Let me tell you. We will start heat transfer through extended surfaces. Tomorrow class, that means 20/11/2022 Sunday, we have class from 1 p.m. to 3 p.m. and we will do heat transfer through extended surfaces, which is basically fins. Okay, extended surfaces. This is the topic that we are. Sir, can you share today the PPT? Yeah, I can share. Of course, I will share. No problem. I can share that. Yeah, I'll share it in an hour or so. Okay. Chalo, okay. So let's meet tomorrow at 1 p.m. Okay. Let's meet tomorrow at 1 p.m. and I will see you tomorrow. Okay. Chalo. Tata, bye bye. Thanks for your time. Solve and solve more questions. Okay. That is the most important thing. Chalo, I am going to end the class. I'll see you tomorrow. Okay. Yes. Thank you. Thank you so much.